Hello? Okay, I think you can hear me. So today I'll be an unhead. There won't be a head of me talking, it will be just a screen. So apologies for that while I try to solve this issue. So let's start with hello world. Good time of day, whether it's morning, afternoon, evening, or night. Let's do a recap. We are doing Introduction to Machine Learning for Coders from Fast.ai, taught by Jeremy Howard. I actually have the link in the description if anyone else is interested to follow along. I was thinking about that the other day, that this Friday it will be 1 full month of me taking this course. I found that quite interesting. So we are currently in lesson 7, which yesterday the instructor was reviewing he was asking questions and I would say almost reviewing things. But we haven't finished the RF from scratch part, which is something we started. So I think we will continue from there. And if we look at lesson 7, there is also the gradient descent based methods. So I think that's going to be really interesting. I'm going to start the video, maybe go back just a bit. Yep, it was like 30 minutes of Q&A almost. Actually, he was going he was going over creating RF from scratch part, like the what do you call it? Random forest, yes. And he was going over that, and then there were a lot of questions, and I think there was a part where he was like, okay, and then I paused it, so I'm going to play it and see what he'll do. I think it's still the continuation of RF from scratch.
Because they won't split. Great. All right.
Yes.
So that's our decision tree. It doesn't do very much, but at least we can create an ensemble.
Yeah, we even have a function where we just pass.
Right, 10 trees, sample size 1,000, right? And we can print out. So now when I go mtrees 0, it doesn't say blah 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 blah. It says what we asked it to say, n colon.
Because we created this function that is almost like toString of Java, I'd say. Yeah.
1,000, val colon 10.8. Oh wait. Okay. And this is.
Shoot, sorry. Just YouTube.
Is a leaf because we have
YouTube refreshing itself because the video is from yesterday. Sorry, that scared me.
Haven't spit on it yet, so we've got nothing more to say. Okay, so then the indexes are all the numbers from 0 to 1,000. Okay, because the base of the tree has everything. This is like everything in the random sample that was passed to it.
So I'm thinking we're saying sample size 1,000.
Remember, by the time.
Sorry. From 0 to 1,000. Sorry, I'm just trying to understand this. I think he's going to explain it. Let me not overthink it. But I'm thinking, how is it random if they're ordered so well? But let's see what he says. Oh, indexes. It's just indexes. So, yeah. Fair. Okay, sorry. My bad.
This is like everything in the random sample that was passed to it. Because remember, by the time we get to the point where it's a decision tree, we don't have to worry about any of the randomness in the random forest anymore. Okay. All right. So let's try to write the thing which finds a split. Okay.
Yep, we have a root, the root itself, but we haven't split on anything. Okay, I'm trying to see if I can like think about it before he does it, even though I don't have information. Because I remember last time when we created the random forest, he was saying that it does every split, and the one where the target is the closest to, like the prediction is closest to the target is the one that we choose. So is that what we're going to do? Is it going to be like exhaustive? I'm actually curious.
So we need to implement find better split. Okay, and so it's going to take the index of a variable number 1, variable number 3, whatever, and it's going to figure out what's the best split point. Is that better than any split we have so far? And for the first variable, the answer will always be yes, because the best one so far is none at all, which is infinity bad. Okay. So let's start by making sure we've got something to compare to. So the thing we're going to compare to will be scikit-learn's random forest. And so we need to make sure that scikit-learn's random forest gets exactly the same data that we have. So we start out by creating Ensemble, grab a tree out of it, and then find out which particular random sample of x and y did this tree use. Okay, and we're going to store them away so that we can pass them to scikit-learn. So we have exactly...
Okay, so we're going to try to create things that are okay, that's cool actually, creating something that works to compare it to. I thought we were going to compare predictions and targets. I guess not.
Okay, the same information. So let's go ahead and now create our random forest using scikit-learn. So one tree, one decision, no bootstrapping, so the whole data set. Right? So this should be exactly the same as the thing that we're going to create, this tree. Okay? So let's try. So we need to define find better split.
This is what we are working on, right? Okay.
Okay, so find better split takes a variable. Okay, so let's define our x independent variables and say, okay, well, it's everything inside our tree, but only those indexes that are in this node, right, which at the top of the tree is everything, right, and just this one variable. Okay, and then for our y's, it's just whatever our dependent variable is at the indexes in this node. Okay, so
okay, I'm gonna need to repeat that, but let me try to repeat it without going back. He said everything inside the tree x values. Oh, there's a lot more happening down here. Okay, so we have x and y, but is this like one row or is it everything?
there's our x and y.
I'm gonna go back. Oh yeah, there's our x and y. I'm gonna go back. I'm sorry.
This one variable. At the variables and say, okay, well, it's everything inside our tree, but only those indexes that are in this node, right?
Okay, so we're in one place.
Which at the top of the tree is everything, right? And just this one variable. Okay? And then
we're sending a variable. Okay, I'm trying really hard to understand this.
and for our y's, it's just whatever our dependent variable is at the indexes in this node. Okay.
Dependent variable being target, as in we have a target, right?
So there's our x and y. So let's now go through every single value in our independent variable. And so I'll show you what's going to happen. So let's say...
So we're actually... Oh, hi! Hello! Oh, wow! That's cool. Really? Oh, yeah, YouTube does allow starting from the beginning, which is pretty cool. How are you? Let me see. I wanted to test something. Maybe not. Maybe I can do it later. Thank you. And welcome. I don't have a head today. Yeah. So we are going to test every... That's what I was going to say. We are going to test every value. Also, how are you?
variable. And so I'll show you what's going to happen. So let's say our independent variable is year made.
Oh. Wait a minute. Independent variable doesn't mean target? Darn it.
And not going to be in order. Right? And so we're going to go to the very first row, and we're going to say, okay, year made here is 3. Right? And so what I'm going to do is I'm going to try and calculate the score if we decided to branch on the number 3. Right? So I need to know which rows are greater than 3, which rows are less than or equal to 3. And they're going to...
Okay, but also I think we also need to... Yeah? Did he say which row is going to be greater than 3 and which row is smaller? Yeah, we can sort it. But my question is, how are we talking to the other rows? Because I saw a loop. Okay, fine, let's loop through it. That we can do. But also, you know, we have to compare the value with everything. That one's like mind-boggling.
going to become my left-hand side and my right-hand side. Right? And then we need a score. Right? So there's lots of scores we could use. So in random forest, we call this the information gain. Right? The information gain is like how much better does our score get because we split it into these two groups of data. There's lots of ways we could calculate it: Gini, cross entropy, root mean squared error, whatever. If you think about it, there is an alternative formulation of root mean squared error which is mathematically the same to within a constant scale, but it's a little bit easier to deal with, which is...
The log?
We're going to try and find a split which causes the two groups to each have as low a standard deviation as possible. Right? So like I want to find a split that puts all the cats over here and all the dogs over here. Right? So if these are all cats and these are all dogs, then this has a standard deviation of 0 and this has a standard deviation of 0. Whereas this is like a totally random mix of cats and dogs, this is a totally random mix of cats and dogs, they're going to have a much higher standard deviation. That makes sense? And so it turns out if you find a split that minimizes those group standard deviations, or specifically the...
I am doing well. Oh, thanks for asking. I'm trying to see how I'm doing. A bit all over the place, to be honest, but mostly good. Like on average, pretty good. Just all over the place. Even like I was like, oh, should I really stream? I was like, yes, I should, because I'm learning. This is for my own good. Yeah, but I'd say a bit tired. Yeah. but good. I'm glad you're good. Sorry, the answer was too long. Maybe you didn't need a answer so long.
Weighted average of the two standard deviations. It's deviations. Or it turns out if you find a split that minimizes those group standard deviations, or specifically the weighted average of the two standard deviations, it's mathematically the same as minimizing the root mean squared error. That's something you can prove.
Maximizing standard deviation is the same as minimizing root mean square error. Cool. I'm gonna see if he actually said that.
Deviations, or specifically the weighted average of the two standard deviations, it's mathematically the same as minimizing the root mean squared error. That's something you can prove to yourself after class if you want to.
Cool.
All right, so we're going to need to find, first of all, split this into two groups. So where's all the stuff that is greater than 3? So greater than 3 is this one, and this one. So we need the standard deviation of that. So let's go ahead and say standard deviation of greater than 3. That one, and that one. Okay?
You can just do standard deviation in Excel sheets? I didn't know that.
And then the next will be the standard deviation of less than or equal to 3. So that would be that one, that one, that one. And then we just take the weighted average of those two.
Okay. Alright. No worries. So now we are in the same reality. Yeah, it's really cool that he explains things with Excel sheets, because like you can see it. But I didn't really know we could do standard deviation. Oh, it's the same. These two numbers are the same. Yeah, I didn't know that you could use Excel sheets for this.
2. And that's our score. That would be our score if we split on 3. Does that make sense? And so then the next step would be try to split on 4, try splitting on 1, try splitting on 6. Redundantly, try splitting on 4 again. Redundantly.
Yeah, because we're doing a blind loop through everything.
Try splitting on 1 again and find out which one works best. So that's our code here, is we're going to go through every row. And so let's say, okay, left-hand side is any values in X that are less than or equal to this particular value. Our right-hand side is every value in X that are greater than this particular value. Okay, so what's the data type that's going to be in LHS and RHS? What are they actually going to contain?
Decimal?
They're going to be arrays. Arrays of what?
Oh, okay.
Arrays of booleans. Yeah. Which
Booleans? Why booleans?
we can treat as 0 and 1. Okay. So LHS will be an array of.
Oh, really? Why? But I mean, oh shoot! Because of the sorry, I see now. Because I was focusing. I wasn't focusing on the. I was focusing on this, but it's the comparison. X with xi. Yeah, of course. We're looping through the whole thing and checking. Yeah, that's fair.
Arrays of what? Okay, so LHS will be an array of false every time it's not less than or equal to, and true otherwise, and
So we're saying left-hand side, right-hand side. Got it.
RHS will be a Boolean array of the opposite. Okay, and now we can't take a standard deviation of an empty set, right? So if there's nothing that's greater than this number, then these will all be false, which means the sum will be 0. Okay.
Okay. So if there's nothing bigger than this, that means we've found it. Do we do the same for the left hand side? Hold up. What did he say?
Right? So if there's nothing that's greater than this number, then these will all be false, which means the sum will be 0. Okay? And in that case, let's not go any further with this step because there's nothing to take the standard deviation of, and it's obviously not a useful split. Okay. So assuming we've got this far, we can now calculate the standard deviation of the left-hand side and of the right-hand side and take the weighted average, or the sum, it's the same thing, to a scalar, right? And so there's our score. And so we can then check, is this better than our best score so far?
So currently, within this loop, do we have like is the self-score, do we save anything in self-score? Because like, if yeah, true evaluates to one false. Yeah. Yes, I've done that for like when you sum up true to see like the percentage. I've done that. You know what I mean, I hope. But I'm thinking within this loop, are we like this is checking with what's before, right? No, X is this index, right? The index that's coming in. So we are checking everything that we have, and then checking with the score of what came in. Am I wrong? Ugh. Just trying to understand it.
And so there's our score. And so we can then check, is this better than our best score so far? And our best score so far, we initially initialized it to infinity.
For each value, check if all values are... Yes. That's the line of left hand side and right hand side. That's that. And then we're doing standard deviation for left and right, doing this thing. Is it weighted average? I don't know. I can go back, but this is our score, and we are comparing it with self-score. So if the score is smaller than self-score, I think we are. Let's see what we're doing.
And so there's our score. And so we can then check, is this better than our best score so far? And our best score so far, we initially initialized it to infinity, right? So initially this is better. So if it's better, let's store away all of the information we need. Which variable has found this better split? We initialized it to infinity, right? So initially this is better. So if it's better, let's store away all of the information we need. Which variable has found this better split? What was the score we found? And what was the value that we split on?
But how are we... So current score should be lower? Oh, we're minimizing standard deviation, are we? No, we're minimizing the RMSE. We're maximizing standard deviation. That's why I'm curious about this line, which I keep repeating, and I feel like I'm losing focus. And I think it's boring how I keep repeating it.
to a scalar, right? And so there's our score. And so we can then check, is this better than our best score so far? And our best score so far, we initialized it to infinity, right? So initially this is better. So if it's better...
How is it being smaller better? Why are we minimizing it?
Let's store away all of the information we need. Which variable has found this better split? What was the score we found? And what was the value that we split on? Okay, so there it is. So if we run that, and I'm using time it, so what time it does is it sees how long this command takes to run, and it tries to give you a kind of statistically valid measure of that. So you can see here it's run it 10 times to get an average, and then it's...
But that's not the MSE. Is it? I thought we were doing, oh shoot, I just realized the chat is hiding his face. I'm gonna put the chat lower. I thought we were, I really thought we were doing standard deviation. Didn't he say minimizing RMSE is like maximizing standard deviation? But is this calculation RMSE? I'm gonna say okay. Anyway, we're doing something here that helps with us saving the current score. But here's my question. We are saving this, and then we're checking again, and then if it's better, we're saving it again. Okay. So, yeah. Okay, we're going through the whole thing every single time. Isn't there a better way to do this?
Done that 7 times to get a mean and standard deviation across runs, and so it's taking me 75 milliseconds plus or minus 10. Okay. So let's check that this works. Find bladder split tree 0. So 0 is year made, 1 is machine hours current meter. So with 1, we got back machine hours current meter 3744 with this score, and then we ran it again.
3744? Like that many splits?
With 0, that's year made, and we got a better score, 658, and split 1970.
The standard deviation measures the dispersion of data points, so the deeper we go in the tree, the more precise we have to be depending on the needed granularity level. Yep. Yeah. No, I'm thinking like, sure we have to go through everything. That's obvious, but is there a better way? I guess having this, if it's 0, then skip is a way to make it more optimized. Yeah. Okay. Looking at the number of splits and our score. Lower score, better. Okay. Yeah, it is. I guess it is RMSE.
4. And so 1974, let's compare. Yep.
It's not R, actually. It's just the MSE, right? Oh, it's MSE. Look, up here. 47, okay.
That was what this tree did as well. Okay, so we've confirmed that this method is giving the same result that sklearn's random forest did.
Cool. Wow, we recreated the same thing.
Okay. And you can also see here the value 10.08, and again matching here the value 10.08. Okay, so we've got something that can find one split. Could you pass that to Yannette, please?
So Jeremy, why don't we put a unique on the X there?
Because I'm not trying to optimize the performance yet.
But you see that, no? Like, he's
That's actually, yeah, he's saying I'm not optimizing for performance. Okay. Because we have duplicates. Why shouldn't we, why should we go through duplicates?
doing more.
Yeah, so it's like you can see in the Excel, I like checked this 1 twice, I checked this 4 twice unnecessarily. Yeah. Okay, so and so Yanette's already thinking about performance, which is good. So tell me, what is the computational complexity of this?
There's one for loop, so I think I'm barely remembering the O notation, but we have ON, and then I think if it's a double for loop, it's ON squared, right? So is this just ON? Or is it, let's see.
Section of the code. And like have a think about it, but also like feel free to talk us through it if you want to kind of think and talk at the same time. So what's the computational complexity of this piece of code? Can I pass it over there? Yes. All right, Jade, take us through your thought process.
I think you have to take each different values through the column to calculate it once to see the splits.
Mm-hmm.
So and then compare all the possible combinations between these different values. So that can be expensive, like because you're.
Can you? Or does somebody else want to tell us the actual computational complexity? So, like, yeah, quite high. Jade's thinking. How high?
I think it's n squared.
Okay, so tell me why is it n squared?
Because for the for loop.
Is it n squared? Wait, am I misremembering? So is one for loop n squared, or is it just n? Oh, I guess, let's see. Maybe I am misremembering.
Loop it is n.
Yes.
And I think I guess the standard deviation will take n, so it's n squared.
Okay, or this one maybe is even easier to know. Like, this is like, which ones are less than xi?
Yeah, 12,
I'm going to have to check every value to see if it's less than xi. Okay,
Mm-hmm.
and so it's useful to know, like, how do I quickly calculate computational complexity? I can guarantee most of the interviews you do are going to ask you to calculate computational complexity on the fly. And it's also like when you're coding, you want it to be second nature. So the technique is basically, is there a loop? Okay, we're obviously doing this n times. Okay, so there's an...
Okay, so I'm remembering that part. Okay. If it's a loop, then it's n times. And...
n involved. Is there a loop inside the loop? If there is, then you need to multiply those two together. In this case, there's not. Is there anything inside the loop that's not a constant time thing? So you might see a sort in there, and you just need to know that sort is n log n, like that should be second nature. If you see a matrix multiply, you need to know what that is. In this case, there are some things that are doing element-wise array operations, right? So keep an eye out for anything where numpy is doing something to every value of an array. In this case, it's checking every value of x against a constant. So it's going to have to do that n times. So to flesh this out into a computational complexity, you just take the number of things in the loop and you multiply it by the highest computational complexity inside the loop. N times n is n squared. You plus that.
Got it. Okay, so I was heading to the right direction, but with the wrong information.
In this case, couldn't we just pre-sort the list and then do like one n log n computation?
There's lots of things we can do to speed this up. So at this stage, it's just like, what is the computational complexity we have? But absolutely, it's certainly not as good as it can be. Okay, so that's where we're going to go next. It's like, all right, n squared is not great, so let's try and make it better. So here's my attempt at making it better. And the idea is this. Okay, who wants to first of all tell me what's the equation for standard deviation?
I don't know, because I don't think I've studied it in English. Maybe I have, but let's see.
Masha, can you grab the box?
So for the standard deviation, it's the difference between the value and its mean. We take a square root of that. We take the power of 2.
Yep.
Then we sum up all of these observations, and we take the square root out of all this sum.
You have to divide by n. So,
Yeah,
yep,
exactly.
yep, great. Good, okay. Now, in practice, we don't normally use that formulation because it kind of requires us calculating, x minus the mean lots of times. Does anybody know the formulation that just requires x and x squared? Anybody happen to know that one? Yes, at the back. Do you want to pass that back there?
Square root of a mean of squares minus square of mean.
Yeah, great. Mean of squares minus the square of the means. All right. So that
sounds like a made up thing. Square of mean minus mean of squares.
That's a really good one, divided by n. That's a really good one to know because, you can now calculate variances or standard deviations of anything. You just have to, first of all, grab the column as it is, the column squared, right? And as long as you've got those stored away somewhere, you can immediately calculate the standard deviation. So the reason...
By the column, do you mean... Oh, the whole thing? So... we calculated for the whole thing. I think I was going for that as well. Is it a mnemonic device or something like that? Yeah.
The reason this is handy for us is that if we first of all sort our data, right? So let's go ahead and sort our data. Then if you think about it, as we kind of start going down one step at a time, right, then each group...
Sort and unique, right? That's like step 1.
It's exactly the same as the previous group on the left-hand side with one more thing in it, and on the right-hand side with one less thing in it. And so given that we just have to keep track of sum of x and sum of x squared, we can just add one more thing to x, one more thing to x squared on the left, and remove one thing on the right. Okay, so we don't have to go through the whole lot each time, and so we can turn this into a order n algorithm. So
I need you to repeat that, sir. Thank you.
Then if you think about it, as we kind of start going down one step at a time, right, then each group is exactly the same as the previous group on the left-hand side with one more thing in it, and on the right-hand side with one less thing.
We shouldn't... What do you mean? Dedupe? Oh, deduplicate? Oh, really? The standard deviation will change? Okay. So just the sorting is enough.
On the left-hand side with one more thing in it, and on the right-hand side with one less thing in it. And so given that we just have to keep track of sum of x and sum of x squared, we can just add one more thing to x, one more thing to x squared on the left, and remove one thing on the right. Okay, so we don't have to go through the whole lot each time, and so we...
I don't get what he's saying by saying remove one more from the right. Yeah. Okay, let's see.
Can turn this into a order n algorithm. So that's all I do here, is I sort the data, right? And I'm going to keep track of the count of things on the right, the sum of things on the right, and the sum of squareds on the right. And initially, everything's on the right-hand side. Okay, so initially n is the count, y sum is the sum on the right, and y squared sum is the sum of squareds on the right. And then nothing is initially on the left, so it's zeros. Okay?
Okay. Okay, trying to focus and see if I can understand this.
And then we just have to loop through each observation, right? And add 1 to the left-hand count, subtract 1 from the right-hand count. Add the value to the left-hand count, subtract it from the right-hand count. Add the value squared to the left-hand, subtract it from the right-hand. Okay? Now, we do need to be careful, though.
Yeah, no, I don't understand. Okay.
Because if we're saying less than or equal to 1, say, we're not stopping here, we're stopping here. Like, we have to have everything in that group. So the other thing I'm going to do is I'm just going to make sure that the next value is not the same as this value. If it is, I'm going to skip over it, right? So I'm just going to double check that this value and the next one aren't the same. Okay? So as long as they're not the same, I can keep going ahead and calculate my standard deviation now, passing in the count, the sum, and the sum squared, right? And there's that formula. Okay? The sum of squared divided by the square of the sum. Sorry, minus.
Oh god. Sum of squared square of the sum. Okay, now I actually understand what's happening here, because you see this is squared, but this was already squared, wasn't it?
That's the square of the sum. Do that for the right-hand side, and so now we can calculate the weighted average score, just like before, and all of these lines are now the same. Okay, so we've turned our order n squared algorithm into an order n algorithm, and in general, stuff like this is going to get you a lot more value than like pushing something onto a Spark cluster, or ordering faster RAM, or using more cores in your CPU, or whatever, right? This is the way you want to be, improving your code, and specifically
Be more resourceful than trying to use more resources. Okay. I mean, it takes energy, but I suppose you should try.
write your code, right, without thinking too much about performance. Run it. Is it fast enough for what you need? Then you're done. If not, profile it, right? So in Jupyter, instead of saying %time it, you say %prun, and it will tell you exactly where the time was spent in your algorithm. And then you can go to the bit that's actually taking the time and think about, like, okay, is this algorithmically as efficient as it can be? Okay, so in
Time it? That's cute.
this case, we run it, and we've gone down from 76 milliseconds to less than 2 milliseconds.
Whoa, the improvement is high.
Now, some people that are new to programming think like, oh great, I've saved 60-something milliseconds. But the point is,
Isn't it like that many folds? It's not just the milliseconds, it's like, it's not even 10 times, it's even more than that.
this is going to get run like tens of millions of times. Okay, so the 76 millisecond version is so slow that it's going to be impractical for any random forest you use in practice, right? Whereas the 1 millisecond version I found is actually quite acceptable. And then check the numbers should be exactly the same as before, and they are. Okay. So now that we have a function, find better split, that does what we want, I want to insert it into my decision tree class. And this is a really cool Python trick. Python does everything dynamically, right? So we can actually say the method called find better split in decision tree is that function I just created. And that like sticks it inside that class. Right? Now, I'll tell you what's slightly confusing about this is that this word here and this word here, they actually have no relationship to each other. They just
Yeah, I mean, I learned about functions in Python being, what do you call it? Was it property? Yes. there's a thing called property in Python where you don't need to write the parentheses. And so this is a function, and this also is a function we made, but I don't know why I don't think we wrote property on it, so I don't know why we're not putting the parentheses here.
Just happen to have the same letters in the same order, right? So like I could call this find better split underscore foo, right? And then I could like call that, right? And call that, right? So now my function is actually called find better split underscore foo, but my method, I'm expecting to call something called...
See, here we wrote property so that we don't need to write the, when we call it, we don't need to write the parentheses.
Decision tree dot find better split, right? So here I could say decision tree dot find better split equals find better split underscore foo. Okay, you see that's the same thing, right? So like
I do see.
It's important to understand how namespaces work. Like in every language that you use, one of the most important things is kind of understanding how it figures out what a name refers to. So this here means find better split as defined inside this class, right? And nowhere else, right? Well, I mean, it's a parent class, but never mind about that. This one here means find better split foo in
the whole sheet.
A global namespace. A lot of languages don't have a global namespace, but Python does. Okay, and so the two are like, even if they happen to have the same letters in the same order, they're not referring in any way to the same thing. Does that make sense? It's like this family over here may have somebody called Jeremy, and my family has somebody called Jeremy, and our names happen to be the same, but we're not the same person. Okay? Great. So now that we've stuck the decision tree...
There seems to be some cuts in the stream. Am I... Like, I'm checking the internet. I wouldn't say it's the best, but there seems to be some cuts. Sorry about that. And also sorry about the sounds. Like, there are way too many sounds around me. Apologies. Can't really do much about it. Guess could have closed the window. I didn't. I'll do that next time. Because it's now getting colder. And it's nice.
The find better split method inside the decision tree with this new definition. When I now call the tree ensemble constructor, right? The tree ensemble constructor called create tree instantiated decision tree. Decision tree called
asked for the better split.
Find var split, which went through every column to see if it could find a better split. And we've now...
Holy shoot. It goes... Yeah? Yeah, the motorcycles are loud. We have a highway really close to us, so... I mean, like, dude, why are you so loud in the morning? And as far as I know, some people make motorcycles loud on purpose. Like, they remove some, components to make it louder, which is annoying. It's like they want to make people annoyed on purpose. I get it, motorcycles are loud to begin with, but they're not as loud as some people make them, which is like making those annoying sounds. Not this just passing by. The ones where like it's like something's exploding. Anywho, so we are going through another ones. No, that's not a motorcycle. That's a truck. Okay. Yeah, we are going through every column, and that's going through every row. So we were right now just running the find better split one, but now if we run the whole ensemble, then performance will like probably be something that we already worried about, but the fact that we already worried about means then it's going to be good. And you see here we said find a better split pass, but then we up there somewhere, or maybe down there. We said, here it is, we made the function for you.
Now defined, find better split, and therefore tree ensemble, when we create it, has gone ahead and done the split. That makes sense. Don't anybody have any questions or uncertainties about that? Like, we're only creating one single split so far. All right, so this is pretty...
Yes? What do you mean we're only creating one single split so far? Isn't that normal? Because we're going through the whole thing.
Pretty neat, right? We kind of just do a little bit at a time, testing everything as we go. And so it's, as you all implement the random forest interpretation techniques, you may want to try programming this way to, like, every step check that, you know, what you're doing matches up with what scikit-learn does, or with a test that you've built or whatever. So at this...
Yes, we did create it little by little. Okay, what else are we doing? Because I feel like I'm running out of time.
Point, we should try to go deeper. Very Inception, right? So let's go now, max depth is 2. And so here is what scikit-learn did.
Oh, we were splitting on one thing. Wait, we have to change our method?
After breaking at year made 74, it then broke at machine hours meter 2956. So we had this thing called find var split, right? We just went through every column and tried to see if there was a better split there, right? But actually, we need to go a bit further than that. Not only do we have to go through every column and see if there's a better split in this node, but then we also have to see whether there's a better split in the left and the right sides that we just created, right? Or in other words, the left-right side and the right-hand side should become decision trees themselves, right? So there's no difference at all between what we do here to create this tree and what we do here to create this tree, other than this one contains 159 samples and this one contains 1,000. So
what we did was just look within the data and choose the best split. But now we're saying we're going another level deeper.
This row of code is exactly the same as we had before, right? And then we check, actually we could do this a little bit easier. We could say if self dot is leaf, right? Would be the same thing. Okay, but I'll just leave it here for now. So is self dot score. So if the score is infinite still, in fact let's write it properly. Yes, leaf. So let's go back up and just remind ourselves, is leaf is self.score equals inf.
Yeah, we're starting off with everything being infinite, and each time we have a value, then the score will become a value, but leaves don't have value, so they're infinite. He said that last time.
Okay. So since it's there, we might as well use it. So if it's a leaf node, then we have nothing further to do, right? So that means we're right at the bottom. There's no split that's been made. Okay, so we don't have to do anything further. On the other hand, if it's not a leaf node, so it's somewhere back earlier on, then we need to split it into the left-hand side and the right-hand side. Now,
what does that mean for columns?
Earlier on, we created a left-hand side and a right-hand side array of booleans, right? Now, better would be to have an array of indexes, and that's because we don't want to have a full array of all the booleans in every single node, right? Because remember, although it doesn't look like there are many nodes when you see a tree of this size, when it's fully expanded, the bottom level, if there's a minimum leaf size of 1, contains the same number of nodes as the entire data set. And so if every one of those contained a full Boolean array of size of the whole data set, you've got squared memory requirements, which would be bad, right? On the other hand, if we just store the indexes of the things in this node, then that's going to get smaller and smaller, okay? So np.non-zero is exactly the same as just this thing which gets the Boolean array, but it turns it into the indexes of the trues. Okay, so this is now a list of indexes for the left-hand side and indexes to the right-hand side. Right? So now that we have the indexes to the left-hand side and the right-hand side, we can now just go ahead and create a decision tree. Right? So there's a decision tree for the left, and there's our decision tree for the right.
Oh. So besides finding better splits, we're doing decision trees for... We're still working with left and right hand sides. Okay. And here we did indexes instead of the zeros and ones, which I do find surprising. Like, how is 0 and 1 that costly?
Okay, and we don't have to do anything else. We've already written these. We already have a function, a constructor that can create a decision tree.
Mm-hmm.
So, like, when you really think about what this is doing, it kind of hurts your head, right? Because the reason...
Thank you. It does hurt my head. My head does hurt. I've been focusing and thinking for the past hour. Thank you.
And the whole reason that find var split got called is because find var split is called by the decision tree constructor. But then the decision tree,
Then it's calling itself again. Yes.
var split itself then calls the decision tree constructor. So we actually have circular recursion.
Which is normally not good. I don't know how good it is in this case. Recursion, avoid it.
And I'm not nearly smart enough to be able to think through recursion, so I just...
Aww. Why are you trying to make me feel better? Dude, you're the one who wrote this.
choose not to, right? Like, I just write what I mean, and then I don't think about it anymore, right? Like, what do I want? Well, to find a variable split, I've got to go through every column, see if there's something better. If it managed to do a split, figure out the left-hand side and the right-hand side, and make them into decision trees. Okay? Like, now trying to think through how these two methods call each other would just drive me crazy, but I don't need to, right? I know I have a decision tree constructor that works, right? I know I have a find var split that works, so that's it, right? That's how I do recursive programming, is by pretending I don't. Just ignore it. That's my advice, right? A lot of you are probably smart enough to be able to think through it better than I can, so that's fine if you can. Right, so now that I've written that, again, I can patch it into the decision tree class. And as soon as I do, the tree ensemble constructor will now use that, right? Because Python's dynamic, right? That's just happens automatically. So now I can check my left-hand side should have 159 samples.
Oh, wow.
Right? And a value of 9.66. There it is, 159 samples,
Yeah, I saw it.
9.66. The right-hand side, 841, 10.15. The left-hand side of the left-hand side, 150 samples, 9.62. 150 samples, 9.62.
Oh.
Okay, so you can see, like, because I'm not nearly clever enough to write machine learning algorithms, like, not only can I not write them correctly the first time, often, like, every single line I write will be wrong, right? So I always start from the assumption that the line of code I just typed is almost certainly wrong.
Yes, I can relate.
And I just have to see why and how, right? And so, like, I just make sure. And so eventually I get to the point where, like, much to my surprise, it's not broken anymore, you know? So here...
So when it works, that's exception case? That's funny.
I can feel like, okay, it would be surprising if all of these things accidentally happen to be exactly the same as scikit-learn, so this is looking pretty good. Okay? So now that we have something that can build a whole tree, we want to have something that can calculate predictions. Right? And so to remind you, we already have something that calculates predictions for a tree ensemble by calling tree.predict, but there is nothing called tree.predict. So we're going to have to write that.
we write methods and we're like, we'll write them someday. So checking the time and checking where we are here, I think we're going to be how long are we going to be doing tree stuff? Reminds me of a programming meme. Doesn't work, I'm not sure why. It works, I'm not sure why. Literally couldn't agree with you. Yeah, that is, yep, yeah, like the first person who, I mean, it wasn't a first person, but the first person who thought, okay, let's make programming a thing. Like, why? Or like people who make programming languages, like where does that come from? How smart do you have to be? I really feel like I should pause here, even though we're about to write the predict function. It's 1:02. If I go forward, predictions, predicting, let's see how much time, predicting, more predictions. Yeah, okay, we're going through this. Hello? Yeah, is this still, yep, this is still the part of the predictions. Yeah, seems like these are all prediction related things. Yep, we're still in the part of the decision tree, I think. We're not, oh yeah, okay, seems like we're stopping somewhere around here, which is almost, yeah, 12 more minutes, and I know 12 more minutes of my time means like 20 minutes, so I think we are going to pause here, for real. Yep, I can't go to the other scene, because there's no one there, so I'll stay on the scene and say thanks for being here. This was informative. My brain is still like spinning, so I don't think I can form, there's a motorcycle, thank you for passing by. I don't think I can form coherent sentences fully, as I'm trying to understand what's happening. But yeah, this was fun. I'd call this a chill stream, but my brain doesn't feel chill. We've been here for, yeah, an hour and 10 minutes. That's pretty okay for a, yes, another one. Oh, there are plenty. Today's a Wednesday, isn't it? Woohoo. Weekends around the corner. Oh wow, you think it's the same one going back and forth? That's actually possible, just so that my stream doesn't, because like sometimes you tune into a stream and you're like, wait, there is no face, the sound is quiet, is anyone even there? But the motorcycle is, background music. Speaking of background music, I was actually thinking of having something like, what was it called? There was something, I forgot. Okay, I'm gonna find it, because I know I sent it to someone quite recently. There's it's not background music, it's God, I forgot. Okay, nope, I shouldn't not found. There we go, a soft murmur, found it. There's a, yes, thank you, ambient sound, not music. No, wow, thank you. The sound were quite the same, so it might be the same, I guess. A soft murmur, it's a website. I made a mix. Oh, I think that's my mix. No, it's not my mix. Let's listen to it. Yeah. And you can dial it up or down, like more thunder, or just zero rain. Just And then there's the one, the coffee shop, which I actually like. Or birds. Yeah. Yep. I had rain and crickets. It's like, no. But honestly, the fire, that one, it's really good. Yeah. So it's like I can have something like this in the background instead of music, because music is, yeah, not something I want to have on stream. Okay. Yeah, now we're in a cafe with a fireplace. Okay, I really gotta end this. Today was fun. Thank you for being here, for helping me study. I hope we can finish this sometime soon, because like we're almost at the end of lesson 7. And when we get to gradient descent, I feel like it's going to be very interesting, because like now I'd like to think we have a base understanding, and then we are going to use more complex things, but also with the, you know, understanding of the style of explanation that Jeremy Harrod does, which is amazing. Okay. I hope you have a lovely rest of your day, and I hope, yeah, it's, you know, you find reasons to smile and enjoy your life. Okay, I'm gonna head out. If you got any, thank you. If you got any questions, let me know. Otherwise, I'm gonna end the stream in 5. I think there is not too much lag, so I can start with 5, 4, 3. Yeah, this motorcycle is making it sound like I'm actually next to a rocket. So maybe there will be a launch. 2, 1. Thank you and goodbye.